Hey y'all, I thought maybe it would be a good idea if I went ahead and made a video of what we started this past week about inverses. Remember, this is what I had you doing with the petty paper and the needles, and you were kind of poking through and seeing what was happening. So I'm going to go through it again and go ahead and finish out the notes, and then hopefully the worksheet will be a little bit easier. Okay, so we talked about what an inverse is. So every function that we know has a potential inverse. And we said, what does it look like on a graph? Right, that's one way to find an inverse. Or separately, what does it look like algebraically? So we said on a graph, and that's what we were doing, two functions are inverses if their graphs are mirror images of each other over the line y equals x. And remember, mirror images, our true math word for that are reflections of each other over the line y equals x. And please keep in mind y equals x is the same as y equals 1x plus 0, right? So that's that line that dashed line that kind of splits the quadrants right in half, right? So that dashed line is our mirror, and our functions need to be reflected over that. And we did that with the patty paper, and I'm going to do it here again in a second. And then we said algebraically, we can tell if two functions, like if we have the two equations, we can tell if they're inverses, if they're compositions. Remember, compositions are where you plug one into the other. Both result in x. So for example, when I find, if my function's f of x equals 3x minus 4, when I find the inverse, I should be able to plug the inverse into f, and I'd get out x when I simplified. Same, and it would work backwards. If I take the original function and put it into its inverse, I should still get out x. Okay, and so we're going to do these both ways. Do some graphing, and do some algebraic work also. So if you remember, the function that I wanted you to do was, on the patty paper, was y equals 3x minus 4. So let me go ahead and put my y-intercept at minus 4. Okay, so I had you draw that on the patty paper with your pencil, right? And then, if you remember, I had you go ahead and take your patty paper off, fold it in half over the line y equals x, right? So there's that line y equals x. And then, once it was folded in half, I had you use the push pins to poke holes all along your original function on the folded patty paper. And what happened is you should have gotten a line that looked something like this when you folded it. And we kind of looked at, okay, what the heck just happened? And you could kind of see that this original point, let's see, this point is 3, 1, 2, 3, 4, 5. This point is 3, 5. If I look across the mirror at its resulting point, that point was 5, 3. If I look at, this guy stayed the same, right? He was started as 2, 2, and he ended as 2, 2 because he was already on the mirror. This guy on my original line was the point 1, negative 1. If I look across the mirror, right, at the resulting point, that's the point negative 1, 1. And then finally, if I look at this, we've got a couple more points on here. This point was 0, negative 4. That was our start point for our line. If I look across the mirror at it, now the point has become negative 4, 0. And I could do this last one. This last point was negative 1, 1, 2, 3, 4, 5, 6, 7. Negative 7. And if I look across the mirror at that point, I would have gotten, this point is negative 7, negative 1. So if you look at
5:25 and 5:30 buses will be leaving in 5 minutes.
Sorry about that.
Make your way to the front of the school so you can catch those buses. The 5:30 buses will be leaving in 5 minutes.
Okay, so on our original function f of x, every xy point that we had on the inverse actually it switched. It became y, x, right? It kind of switched. Every point switched spots. Okay, and what I had asked you right at the end was this new inverse, and this is our notation. We call that f inverse of x. I wanted to know what's its equation. So if you look at that, we can see on that dashed blue line that our slope is 1/3, right, and we're rising. And it doesn't have a perfect y-intercept, so I'm just going to pick a point here to plug in. I'm going to take that first one we looked at, that first inverse point, 5, 3. So this would be x minus 5. Oop, I ran out of room. Scooch that over. X minus 5 plus 3. And we said that that was our inverse function, right? So we had f inverse of x equaled 1/3 x minus 5 plus 3. Right? And I don't think that's exactly what I did in class, but the same point I picked. But I know that we did distribute this out to make it into slope-intercept form. So that was 1/3 x minus 5/3 plus 3. And if I combine those like terms, negative 5/3 and a positive 3 actually ends up giving us, let's see, 3 is the same as 9/3, so that'd be a positive 4/3. Right? So f inverse of x in slope-intercept form is 1/3 x plus 4/3. Okay. So we know what it looks like graphically, right? We had that graphical image of what it meant to be an inverse, kind of reflected over the line y equals x. That was our mirror. Algebraically, though, remember what we said algebraically was that if I take an inverse and plug it into the original function, I should get out x. So keep in mind our original f of x was 3x minus 4, right? So we should be able to check their function composition. So firstly, I want to check what happens when I take f inverse of x and plug it in to f of x. So that's what this first thing is. F inverse of x is on the inside. So I've got my 3x minus 4, but where I had the x, I want to take that out and put the inverse in its place. So I've put f inverse in for x. And then just go ahead and there we go. Go ahead and distribute that out. So 3 times 1/3 is just 1. 3 times 4/3 is just 4. And then x plus 4 minus 4 simplifies to just x. That's what I was talking about. We're supposed to get out x. It's supposed to simplify that way. Okay, so now let's check it the other way. What if instead of putting f inverse inside, I take f and put it inside f inverse? That's this one, regular function inside of its inverse. So now I've got the fraction function on the outside, and inside of the fraction function, I've got the original 3x minus 4. Again, just distribute that out. So 1/3 times 3x is just 1x. 1/3 times negative 4 is negative 4/3. And then that negative 4/3 and that positive 4/3 will cancel to x. This is how we know we're right. That the inverse of 3x minus 4 is 1/3 x plus 4/3. Okay, so graphically, it's a reflection over the line y equals x, that fold mark. Algebraically, when you plug them into each other, you should get out x. Okay, so this was just a linear, right? Just a plain linear, which is pretty easy to work with. That's why we always do linears first. And then right at the end of the class, remember I had said, really quickly, can we try and get this quadratic graphed? And so this is what it would look like. So let me go back to that. Let's see, the turning point. So the turning point of this is at -3, -5, right? And then my rate of change up there is a 1. So I know my first stair step will be up 1. And then after that, my first stair step from my turning point will be up 1. And then my next stair step, I have to change by, my ROC will be changing by 2. So 2 more than 1 would be +3, then 2 more than that would be +5, right? So it's going to look something like that. So I went ahead and did that. So here's my function. Let me go ahead and put it where it's supposed to go. We said the vertex is at -3, -5. If you notice, my first stair step size is 1, my second stair step size is 3, and then it gets a little off after that. That's a smartboard limitation. Anyway, so here's my function. And if we were to do this on patty paper, and if you were to draw this, fold along the fold mark and use your push pins, you'd get this guy. Let's see, I need that guy to be reflected right there. Oop, a little bit further down maybe. Ah. Yeah. Okay. And so what it does is it reflects. So let me just show our points again. So this turning point, remember that point was -3, -5. That should have switched. So this point is -5, -3, right? If I take another point, this point, my first stair step up, let's make that green. My first stair step up, that point is -2, -4. So if I look across my mirror, I should find a point at -4, -2, right? Everything gets reflected. And then any points that were already on the reflection line will still be on the reflection line, right? Because when you switch them, it's still the same. Okay, but here's the hard part. So this guy flipped on his side. What's the equation of that inverse? So when you look at this guy flipped on his side, what's the equation of that? Well, it's not a function. Remember, in order to be a function, it's not passing that vertical line test, right? We have points that are overlapping each other, and that is not okay to be a function. It's not passing the vertical line test. So actually, I want to look at what we do with this algebraically. I'm going to tell you how we handle this, because it's not really a function the way it is. So I want to use the idea, so we're going to go through and figure out what the heck is the inverse of this function. And I think I had shown you these right at the end of class. Maybe not. We'll go through them anyway. So in order to find the equation of an inverse, you take that original f of x. I'm going to just take our linear from earlier. You take that original f of x, replace it back with a y. Then we know that every ordered pair, when we do the inverse, every y becomes x, every x becomes y. So step 2 says interchange. So make the x in the y spot, make the y in the x spot. And then it says solve for y. Okay, so I'd add the 4 over. I'd get 3y, solve for y, divide by 3, so I'd have 1/3 x plus 4/3 equals y. And that was our inverse. Step 3 says, okay, go ahead and replace the y back with f inverse of x. And I'm going to write this in order. Normally we write that first. We've got our 1/3 x plus 4/3, right? And then it says now verify. So do your compositions. Well, we already did. We know that when we plug these into each other, we get out x. But it's very simple to do, or to find the inverse algebraically. You just switch x and y and then solve. So let's go back to this. How do we find the equation of what the heck's going on with this sideways quadratic? Let's look at what happens when we switch x and y. So I went ahead and I did the steps. I took our original function, I put y back in, right? Switched x and y, and now I'm starting to solve. So I need to get y by itself. So the 5 has to go, the -5 has to go, so I added it to the other side. Then our square has to go, so how do we get rid of a square? You know that we square root. Don't forget the plus minus, right? And then, to get y by itself, we subtract the 3 over. Whoops, we subtract the 3 over. There we go. So here's the deal. Oh, and then we would try and go back and replace that last step with f of x. But we know this is not a function, so we can't put it in function notation. So I can't even write f inverse of x. Except if I split this and say that y is -3 plus root x plus 5, and separately y is -3 minus root x plus 5. Let me tell you about this. This guy, the one that has the positive root, this represents the upper half of the sideways parabola. This guy with the negative root represents the lower half. of the sideways parabola. And these are what we call square root functions. They're sideways, they're inverses of quadratics, so they're sideways quadratics, but we have to break them apart in order to be true functions. So really, when I'm asking you what's the equation of this inverse, well, this top half has its own equation that was y equals -3 plus root x plus 5. And this guy has its own separate equation, y equals -3 minus root x plus 5. We cannot have them both at the same time or we wouldn't have a true function. Now we are going to seriously study these square root functions second semester. For right now, I just need you to know how to get something by itself and tell me the pieces of the inverse. So this is really kind of like, what's the equation of the inverse? This is kind of a trick question because you're going to have to give me both parts, the -3 plus root x plus 5 and the y equals -3 minus root x plus 5. And that's just for quadratics because when we reflect over the over the line y equals x, we get a not function. This would also happen with absolute values if I asked you to do that. Okay, so I've got another example in here about finding the inverse algebraically, but I don't think we need to go through it. I think you guys are okay with if I switch x and y, then solve for y, then I should be able to get the inverse. So that's all this one was. I'll just flash it up here really quickly. I went ahead and replaced f of x with y, switched x and y, solved, so then I had my inverse, or what I thought was my inverse. So here was my original. I did all those solving steps. Here's what I thought was my inverse. And then remember, if I want to check, how do I know if I'm correct? You want to check the compositions. Does f inverse of x equal x, and does f of f inverse equal x, and does f inverse of x equal x? So I checked both of those. So here's my work checking where I plugged one into the other and vice versa, and they both did equal x. So that's just a simple example, and there's no need to write it down if you don't want to. But I did want to put this one up. Suppose instead of asking you to find an inverse algebraically, where you use the equation and switch x and y, suppose I ask you to do it graphically. So I don't have an equation up here, but I still want the inverse. So here you need to remember that every xy, you need to make it become a y comma x, right? Because the x and the y switch. So if I've got this point, my first point, I'm going to try and change color so that we can kind of make sure we're saying consistent. 1, 2, 3, 4, 5, 6. This is the point, -6, 0. So I know -6, 0 is going to become, in my inverse, it's going to become 0, -6, right? 0, -1, 2, 3, 4, 5, 6. And I know that my next point, this guy is -4, 4. So that's going to become -4, 4 is going to become, switch that, 4, -4. So over 4, down 4. So here. So far I'm there. Then, let's see, I've got the point. My next point is 1, 4. So I know that 1, 4 is going to become 4, 1. 4, 1. So here is my next spot, right? Let's see, I need a new color. Let's be purple. So next point is here. That point is 3, -5. So that would become -5, 3. -1, 2, 3, 4, 5. And +3, right? So that's here. And then, last point, I need another color. Let's go, can we see yellow? Let's try it. This last point is yellow. That point is 8, 1. If I switch, that would be 1, 8. Right? So 1, 8 is up here. And there's my last piece. So this guy, and again, if you had patty paper, it would have been great. You could have push pinned this and done it that way, but since we don't, we have to switch our points, right? Now, if you think about it, is this new guy, is it a function? Definitely not. It definitely overlaps in multiple places. Particularly at this spot, it overlaps 3 times, right? So it's definitely not a function. But I do want to just make sure that you know what's going on when we switch x's and y's. Okay, so you can do it from a graph, or technically, you should be able to do it from an equation where you replace y with x. And just switch and solve, or you can do it from a graph where you just switch. Okay, hopefully that was more helpful. You should be able to do the worksheet perfectly well at the